All right, guys. So this is the final part of going over, whoops, going over the multiple choice practice test. Um, and again, this is from the 2014 international exam. So this is the test that the international students took back in 2014. So it's an actual AP test. So, and we left off. We were on question 42. Okay. And this, this is one question. It's asking what is this alloy going to look like? And we have an alloy, and it's got iron and carbon. So remember, iron and carbon is interstitial. All right, so because carbon is much smaller than iron, but it's got elemental chromium added to the steel to make steel less likely to rust. So, okay, so the chromium is going to be on the surface of the steel to oxidize with oxygen so that the iron doesn't oxidize with oxygen, right? And so they want us to be able to look at the surface of the alloy, be able to picture the surface of the alloy, and be able to picture the interior of the alloy. Okay, so the surface is going to be where oxygen's getting involved, but you're hoping that the oxygen is hanging out with the chromium that's there. Chromium and iron should be drawn with a similar size radius based on this chart here, right? And then the interstitial interior, right? We should see some chromium, but we should see some carbon in between there, but no oxygen in the interior of the steel, and that's what's going to make the steel strong. So if we look at some of this, right, like this doesn't show any chromium and no chromium here. Okay, so this might be like might be a nice picture of high carbon steel here, but it doesn't. It's missing the chromium. Okay, has the chromium, so B is the right answer. This one's incorrect because it shows small chromiums, right? Too small, and this was wrong because it's showing oxygen getting into the interior, and the whole reason you put chromium on the surface is to block the oxygen from getting into the interior with the iron. Okay, so choice B is your answer here. All right, so let's go to 43. All right, so remember, if natural log of concentration versus time gives you a straight line, you know you have first order kinetics. So Z is first order. And look at the question. The order of the reaction with respect to Z is first order, B. Okay. So just remember our kinetics. If this had been a straight line, but it was just concentration versus time, that would be zero order. If this was a straight line and it was 1 over the concentration of Z versus time, that's when you have second order. But the natural log of concentration versus time giving you a straight line, that means that reactant is first order. Okay. All right, so here we got a reaction, we got pathway 1, we got pathway 2. Pathway 2 is the catalyzed pathway. Our delta H is positive 50, right, because the products are higher in energy. 150 here would be our activation energy for the uncatalyzed reaction. So kind of a lot going on here. We know it's endothermic, so heat is a product, all that good stuff. All right, so which of the following most likely accounts for the difference between reaction path 1 and path 2? So presence of a catalyst in path 2, so D, okay, for 44. 44 is D. All right, which of the following best describes the flow of heat when 1 mole of XY2 decomposes? Well, we know it's endothermic, so heat is absorbed by the reaction system, which means heat is lost by the surroundings. So, and if it's 1 mole of this, the delta H of the reaction is 50 kilojoules per mole of reaction. So when 1 mole of this decomposes, 50 moles of energy is transferred from the surroundings. So it would be choice B, from the surroundings. And if it's from the surroundings, it means it's to the system, right? Okay, so if this had been exothermic and it was a negative delta H instead, then the correct answer would be A. But because energy is being absorbed from the surroundings to the system, that much energy is transferred from the surroundings. So I'd rather say 50 kilojoules of energy is lost by the surroundings, but whatever, doesn't matter. Okay, number 46, the reaction is thermodynamically favorable under standard conditions, right? And so that must mean delta S is positive, because you can't have a positive delta H and have a negative delta S and the reaction is never favorable, if that's the case, right? So if you have a positive delta H and the reaction is favorable, which they're telling us in question in 46 here, that means delta S must be positive. But remember, it's got to make sure that delta G gets negative, so that means delta S has to be greater than delta H divided by the temperature, right? Because you're thinking delta G equals delta H minus T delta S, right? So you're filling this equation. So that must mean delta S is actually greater than delta H divided by the temperature. And that'll give you a negative number, which means thermodynamically favored. So initially, right off the bat, I was like, okay, delta S has to be positive, but it's got to give us a little bit better, right? So we know it's not equal to 0. We know it's not equal to that because then delta G would be 0. If it said they were both the forward and the reverse reaction were equally favored, then the answer would be B. And it can't be less than, because if it was less than, then you would end up with a positive delta G according to our delta G equation here. So it's got to be C. All right. All right, so we're looking for an ionic crystal. So just real quick, C is, remember, the way they structure a metal, right, with the nuclei next to each other and then the electrons free flowing, right? C is a metal, so we know it's not C. D would be maybe a polar covalent solid. Or, yeah, it looks like, not a polar covalent, non-polar, it looks like a hydrocarbon, basically. So big, long carbon chains here. So this is covalent, clearly. So it's either got to be B or A. And remember, a cleavage point or brittleness is when you apply pressure to the crystal, and then that forces the negative ions to line up next to each other and the positive ions next to each other, and then they break apart because they repel each other. So before and after, negative next to negative, positive next to positive. So choice A for 47. Okay. All right. A couple more problems. All right. So here we have this reaction: 6 moles of propane and 20 moles of chlorine react, and they want to know how many moles of HCl will be produced. So this is limiting reactant stoich. So 20 moles, if 20 moles of chlorine react, it's a 4-to-4 ratio or 1-to-1 ratio with HCl, so that could give you 20 moles of HCl. But if 6 moles of propane react, then what's 6 times 4 over 1, you could get 24 moles. So propane would be our excess reactant and chlorine would be the limiting, so we're only going to be able to get 20 moles of the HCl. So which number was that? 48. So 48 should be 20 moles, which was choice C. Okay. All right. So here we got acetone, 1-propanol, butane. They give us the structure. So what we got to notice is, hey, this is polar, but just dipole-dipole interactions because it doesn't have a Fon bond. This is polar with hydrogen bonding because we do have a Fon bond. And this is just a hydrocarbon, so non-polar. So if we're ranking in terms of IMFs, this only has London dispersion, this has dipole-dipole, but this has hydrogen bonding. So we would expect the propanol to have the highest boiling point and the butane to have the lowest boiling point. So that would be choice B. Butane has the lowest boiling point of the 3, and propanol has the highest. Okay, all about IMFs there for 49. Okay, last question. All right, so we have a reaction mechanism. The reaction represented above occurs in a single step, so it's an elementary step. So this is the mechanism. A scientist correctly calculates the rate of collisions between NO and NO3 that have a sufficient energy to overcome the activation energy. The observed reaction rate is only a small fraction of the calculated collision rate. Which of the following best explains it? Because just because it has the right energy doesn't mean the collision has the right orientation. So the scientist here didn't account for proper orientation. So the two reactant particles must collide with particular orientation in order to react. So B. So remember, two things have to be true about the collision. You have to have the right energy, but you also have to have the right orientation. So he was just looking at the collisions that might have the right energy, but didn't factor in that all those collisions will not have the proper orientation. So it's not going to, the reaction is not going to happen as fast as just the number of collisions that have the correct energy. Okay, so choice B for that one. Collision theory. All right. All right. All right. So that takes us through that entire practice test. So hopefully, as you're starting to prepare for your AP exam and your final exam, watching videos like this are helping you review and, you know, get those final touches in. And really, you want to look as many practice tests as possible, just so you get used to how, you know, College Board is asking their questions, and you know, to watch out. Like there's always like certain little tricks they like to pull. Like they give you this big long-winded question, like that one question with the piston from part 1, and it had nothing to do with Boyle's law. It had nothing. It's just that you had to know that they said temperature was constant, so average kinetic energy remained the same, and that was it. So it's just like little things like that. Just watch out for the normal tricks that they try to pull. You know, watch out for trap answers, right? Read the question, but read it fast. And then if you get hung up on something, don't spend too much time on it. You got a calculator now, so you don't have to sit there wasting your time worrying about, you know, mental math. You know, if you're like, I don't want to do that calculation in my head, do it with your calculator, okay? It's not that big of a deal. All right, so hopefully that helps, and happy review. All right, good luck.